My guest today is Dr. Peter Vereš, who is research scientist at Harvard-Smithsonian Center for Astrophysics at the Minor Planet Center. Minor Planet Center, MPC, is the official worldwide organization in charge of collecting observational data of minor planets, calculating their orbits, computing their trajectories, announcing discoveries, and publishing the data. Welcome, Peter.
Hi, how are you? Thank you for having me here.
Yeah, so thanks for doing this. Our topic today is planetary defense, discovery and characterization of near-Earth objects, and possibilities to protect the Earth against the cosmic collisions. So near-Earth objects are things that are sort of flying around closer to us, away from the asteroid belt, right? It's much closer to Earth.
Indeed, as you may know, most of the asteroids that we ever discovered are really located between the orbits of Mars and Jupiter. So basically, at this moment, we have like around 1 million objects on known orbits between. There's a number of objects that are much close to the Earth, and these objects are called near-Earth objects or near-Earth asteroids, if they are asteroids, not the comets. So currently, we know more than 26,000 of them, and the number is up every single.
Could you repeat that, Peter? You froze a little bit. Currently, we know how many?
Currently, we know 26,000 near-Earth objects. I would say 26,500, and this number is going up every single day.
Yeah, so if you look at the demographics of these asteroid-type objects, so something that is, let's say, 100 kilometers or higher is sort of like a minor planet, right? It's a dwarf planet or something like that. So if something like that hit us, that is probably, you don't have to go to the airport the next day. That will probably be final. But then dinosaurs got hit by something that is more like 10 kilometers in size, right? And that is a real disaster for the entire planet, something at 10 kilometers in size.
Yes, correct. So basically, objects that are a few kilometers across are very rare to impact the Earth. So in terms of like an asteroid killer that killed dinosaurs or large animals like 60 million years ago, that frequency is very low. It happens like once per, let's say, 50 million years. So we are more endangered by objects that are much smaller. So I would say we should be more careful about objects that are a few hundred meters across, up to 1 kilometer, because their frequency is much larger in terms of our risk Earth impact. And also on the other hand, because we know pretty much all the large near-Earth objects, it means like we know their orbits, we can predict where they are in the next decades or centuries. We are safe from those. So
okay, so something a few kilometers wide, the chances are quite low. We already know what they are. They're big enough for us to find. But it is, like you say, it's the things like in the tens of meters or hundreds of meters in size that is really problematic. They're tough to find, right? That's the issue.
Exactly. The smaller the object, it must be much closer to the Earth to be detected. So basically, we have a much shorter warning time. And basically, that's the goal of the planetary defense. So I would say that's the easiest, because one trying to defend us if we find something. So the cheapest and most kind of smartest way to do right now is to discover them all. And if you have like the old population, then you are pretty much safe because you are. You go from the largest one because you discover them first, and then go slower and slower into the smaller parts of the sizes.
So why are the near-Earth objects? Why are they smaller? What is the mechanism there?
So basically the distribution follows basically size frequency distribution. It's similar when you take basically a pile of dirt or sand from a sand pit, basically, and you will have a small number of those large pebbles, but then you go smaller and smaller for the smaller ones like the sand. You have really large quantities. So it seems for the near objects or asteroids to do the they were formed. So basically at the beginning you had like, I would say, thousands or several thousands of large objects, but you had collisions that were happening like billions years ago. They basically destruct. So it's a destruction that was happening for the last 4.5 billion years that basically grinded objects into smaller pieces. So when we are talking about objects that are basically a few meters or fragments of once much larger bodies.
Right. Yeah. So as time goes on, they collide with each other. They get smaller, and the real small ones are always falling onto Earth too. We just don't notice them, right?
Exactly. So as I mentioned, it's a size frequency distribution. As I mentioned, the smaller the size, the higher the frequency, because it's much larger. So when we go to the really tiny ones, let's talk about 1 meter in size. You can imagine that's a small thing. It's a comparable to size of a small office desk, right? So these objects basically frequently, I would say like 30 to 40 objects per year. But those are small, so basically only small pieces of them impact the Earth of form of meteorites, and you can see them on the sky as bright fireballs. So that's a spectacular event, but they do not pose and so ever because they burn in the atmosphere, most of them. But if we are going to the larger sizes, let's talk about the sizes that we really encountered in the recent history, like the Chelyabinsk event in 2013 in Russia. It was like only 20 meters in size. See, it's still in the meters, it's not even kilometers when we are talking about the planetary killers. That frequency is, let's say, once per few decades, once per 50 years. If we go even from like 100 years ago, we are talking about even that is one per hundreds of years. So that's the approximate frequency of the collisions with the Earth.
So in the last, let's say, few hundred years, what is the largest object that we know of that collided with the Earth?
I would say it was the Tunguska event, even though it was a long time ago. So basically it was in 1908. And the problem is there was no meteor or impact crater found on the surface, and the expedition that went to the site, which was deeply in Siberia, arrived there many years ago, didn't find anything. So which actually sparked very interesting interest of scientists and geologists to figure out what happened. And they actually concluded that most likely explanation was this similar to Tunguska, but the blast was much larger than in case of the event near Chelyabinsk. So it's like you don't even need the object to impact the surface, creating crater, to cause a major damage on the surface. So that's an interesting physical phenomena that's on the boundary between objects that are too small to cause any damage and much larger to actually impact the surface and creating crater on the surface.
And so those explosions that happens in the midair is also quite damaging. And so if I understand this correctly, Peter, the smaller ones sort of get vaporized as they fall through. The larger ones have enough mass to actually impact the Earth, and somewhere in between there are things that gets burned out. But then that process itself is quite damaging from the kind of the buildings and all of those things, right? When that explosion happens.
Exactly. When I need to describe, let's say, the blast that reaches the surface of the Earth, it's not just the high winds you have the overpressure and also the temperature, because of the moment of, let's say, the explosion that happens in the atmosphere above the sea level. The shock wave basically reaches the surface of the Earth, so it can have a lot of heat as well, not just the wind, basically, or the change in the pressure. So, for instance, we have evidence from history that is kind of more in the past, like people didn't see it with their eyes, but you could find like places in the desert, like I think in Saudi Arabia and in Africa, in northern Africa. They basically found evidence of the molten of the surface of the desert, of the silica. So something happened there, something like an explosion, basically, that caused the of the silicates on the surface, and we believe those were the explosions of the meteorites in the atmosphere. So it is believed it was kind of similar in terms of Tunguska, even in Russia, like 100 years ago. So this hit the surface of the Earth. And one of the reasons could be that the object was not made of metal, so it was like a metallic object that would survive the large overpressure. So it was either consisting of like nose part, the carbonaceous meteorite, or it was a piece of a comet, possibly. So it was very fragile, but it was still massive. So it's not mostly about the mass. The kinetic energy is proportional to the velocity that causes the kinetic energy to transfer into, let's say, heat or explosion. So I would say if we return back only like 8 years to the past, to Russia, to Chelyabinsk in 2000, again, the hit the surface of the Earth. Basically, it exploded like 30 kilometers, more than 30 kilometers above the surface. But what caused the damage was the shock wave, was the blast. And more than 1,000 people were actually, there was a lot of damage on the surface. But most of the injuries came from basically the windows and the shattering of the glass. So people saw this phenomena on the sky, which was amazing. All of them went to the window, staring out windows. And as they were staring, of course, the shock wave reached the surface, and all the glass shattered. So you had like hundreds of people going into emergency rooms with really from. They basically got from the shock wave. So that tells you like you don't even need an object hitting the surface. You just need it exploding in the atmosphere. So that's why that was one of the reasons why NASA moved the limit of the dangerous objects from 140 down to probably 30 to 50 meters that we should be worried about.
And so at Harvard-Smithsonian, you have this minor planet center. So what is the definition of a minor planet?
That's a good question, basically. So minor planet is a very, very broad term, and you can basically understand asteroids as minor planets. You can even understand comets as minor planets, and we even classify or have orbits and observations of satellites of small out of major. So minor planet is something that is much smaller than a planet. It's basically smaller than a dwarf planet, but it's still a macroscopic object. It's not like a meteorite. It's not like micrometeorite. It's not. So planets, I would say, are macroscopic objects, not microscopic objects, that you can still observe from the surface of the Earth in space, but that are smaller than planets.
So are they spherical in shape? Typically?
I would say very. No, not at all. So basically, maybe you remember the famous Congress in Prague where people were demoted from a planet down to the new category planets. And one of the categories, one of the criteria was having a spherical shape, which Pluto has a spherical shape. That's not a problem. And the spherical shape is basically achieved by the total mass of the body. Basically, the mass is to form the body into the form of sphere, because there is some kind of a solidification process that can solidify the surface, and basically it can melt the center, the core of the planet. So you can logically get a sphere. Asteroids are much smaller, so they never had enough internal heat to actually form into a planet-like body that is spherical. So that's why they often have shapes that are irregular, and especially if we are talking, they are much smaller. Like if you have an object that is smaller than hundreds of kilometers in size, it's usually a piece of debris from a past collision that didn't form back into any spherical shape.
Right. And I know that there was an extrasolar object that came through. I can't quite pronounce its name. It's a Hawaiian name.
I can.
Yeah, and so the shape of that appears very unusual, right? So we don't see shapes of that type of shape within sort of within the solar system, right? So what is the conjecture there? Why do we see something such a long, narrow type object?
You are definitely right. Oumuamua was the first discovered interstellar objects or papers before I was one of the co-authors of one of the papers, like theoretical papers, predicting objects like this will come, and we will detect them with telescopes like Pan-STARRS in Hawaii, where I worked in. So it was really discovered in 2017, and I was at the MPC where we were basically receiving the first data of an object that suddenly appeared to be on hyperbolic orbit, which was really strongly hyperbolic. And so really, this is in the measurements or really large uncertainties on the positions, it's really on hyperbolic orbit. So maybe that's the first few days of the observations of Oumuamua, how we saw it at the Planet. But you are kind of became apparent that the light curve of the objects is really weird or interesting. So it was changing its brightness so rapidly in terms of, I think in terms of magnitude, which is the measure of the brightness of the stars or cosmic, it was more than 2 magnitudes. So it was apparent there is a big difference between the long and the short axis of the body. So usually this is used to determine how elongated are the asteroids. As I mentioned, asteroids are not spherical. They're often having shapes like elongated shapes or even shapes of a dog bone or some shards of a former body. From the light curve, from the light curves, you can kind of reconstruct the shape. Or roughly you can even easily say like it's elongated to this extent. This is the kind of eccentricity of the ellipse. So you can fit the shape. But for Oumuamua, it was so extreme. The object is 10 times as longer than wider. So that's kind of gave impression to artists who draw Oumuamua. First idea, this is basically a very elongated ellipsoid, which it was really difficult to imagine how this even formed, right? Like what kind of process, what kind of collision. It's basically almost impossible to the collision in the solar system. Why these objects look like that. But the problem we have even until nowadays is that basically it's only derived shape. So we really don't know how it looks like. And there is a second form how it would look like. So it's not like an ellipsoid, it could be a disk. So basically it can be an object that looks like a flat pancake. So it's either a long cigar, it's kind of a flat pancake. That's all you can say based on the light curves we have. And it's also worth mentioning, we only saw it for a very short time. It was observed only for 2 months. And then it was just too far. It was the largest telescope. So we only had a very short time to look at it.
Yeah, there was some speculation, and I think this is continuing, that it was an extraterrestrial vehicle of some sort taking a few pictures. What is the status on that? Has that conjecture been rejected, or there is something to it?
There are so many this object, even though it was observed so shortly, and we didn't have that much data, unfortunately, on it. I think the SETI Institute even pointed the radio telescope of this object to if there is transmission going on, but there was nothing. So that's negative from at least this point of view. But in terms of the theories we have, I most like the theories that are kind of natural explanations toward using physics. And the latest one I basically read was about trying to explain it as an object that was made of ice. I think the last was like the nitrogen ice. You could have a kind of analog in the solar system. You can take a look at the surface of which is a surface that is made of nitrogen ices. Then they need to be really at a very cold temperatures, under minus 200 degrees, basically Celsius, to stay in the solid state. So perhaps it was a shard of a minor planet in another solar system that is far, far away that was similar like Pluto, very far from its parent. And this piece of ice was just traveling through the space for billions of years. And slowly, because of the bombardment of the cosmic particles, its shape changed to this elongated form. And as a solar system, it is even expected that the shape became even more extreme and even lost some part of its mass while it was flowing through the solar system. And one of the mystery was we didn't see any activity. Because the first, it's a comet. Its motion was not really following the Keplerian motion, like, the basic three Keplerian laws and just the Newtonian motion around the sun, it was accelerating. And we have experience from the sun, comets are objects that are accelerating because they have gases escaping their surfaces. And you can compute basically like the three components of the velocity that is basically increase the velocity of the comet, because you could actually see it. You could see the activity, you could see the coma, you could see the tail. So you can compute the amount of mass that is escaping the surface, not just in the form of like CO2 vapor, but also the dust you see. It's a mass that is really escaping the comet's surface. But in case of Oumuamua, you could describe there is some kind of acceleration, but there was no evidence of any activity whatsoever. So it was moving irrational, and you didn't. So that's why I like the theory about the nitrogen gas, because for nitrogen, I wouldn't say even evaporating, it's basically the solid state turning into gas instantaneously in the solar system. You wouldn't see it in those amounts because that object was small. It was probably 20, 30 times 100 or 200 meter size object. So that's one of the plausible theories that look reasonable to me at this point.
So from a planetary defense perspective, you are cataloging all these near-Earth objects. We are getting a better and better understanding of how many are there. We still don't have a full picture. But from a risk perspective, these types of objects, they're going to be highly infrequent, I would imagine. They don't really pose a threat, right?
Oh, of course, exactly. So basically every year, like let's say the previous covering 1,000 near-Earth objects per year. So that's the number. And that's only possible because of the activities that most of the United States are doing in terms of planetary defense and for observation, really are specialized in searching for these objects. And all of these objects that we know pose no threat to Earth because, number one, we know their orbits mostly very well, but of course the orbits. But once the object is discovered, discovery means you see it for the first time, but then you follow it up for a few days, at least for a few days, to have an idea what the orbit looks like. So in that way, you can predict where this object will be in a year, 10 years, 100 years from now. So you could see immediately after a few days, this is not a threat for the Earth. So you have the orbit, you have designation for an object, so that object will start to exist for the entire world and community. And the Minor Planet Center is basically an institution that gives these observations and orbits freely public. It's not kept immediately after object is discovered, it's out publicly. So not just the scientists, but people around the world can go to our website and just get the information about every single object. So, and they're observe them. So I always say the danger is currently coming from objects we don't know. So we can know from the frequency of discoveries as a function of size, how many objects discovered in a given size range. So when we go back to the near-Earth objects, as I mentioned, there are many small ones, but the numbers of the large ones are small. So currently, about 1,000 objects near the Earth, in the near-Earth space, they are larger than 1 kilometer in size. And we know about 95% of them. And that was one of the original mandate of the US Congress to NASA, State 8, that NASA should really find like all of these large objects in the next decade, and they really did it. So basically, in 10 years, in 2008, we could say like 90 objects larger than 1 km in the near-Earth space. So in 2008, the NASA's mandates changed, and so they were told, okay, you were really doing a great job in finding these large objects. Let's focus on the smaller ones. Let's focus on objects larger than 140 meters. Let's find these in the next 10 years. And basically what happened now is 2021, 2008 was 2018 was like 10 years after the deadline. we are still only at 40%. So for the objects larger than 140 meters in size, we are still not knowing about 60% of them. So that's where the danger is coming from.
So objects greater than 140 meters, even at that size, they could take out a city, right? Potentially, if it falls to a city.
That's correct, and that's one of the reasons these new missions that are visiting asteroids, nearer asteroids like OSIRIS-REx or Hayabusa 2, we're going to objects regime. So asteroid Bennu or Yugu have like 700 meters in size, and in the similar size regime is the asteroids that is going to visit it next year by the DART mission, the planetary. Objects from close from the spacecraft, how they really look like, what is their physics, because those are the objects that could pose the threat to Earth. But I have to also mention that statistically, it's still a pretty low chance that size of the Earth, right, in the next 10,000. So we will be really unlucky if that happens. But it's better be safe than sorry, and just it's much better to discover them, just with the observe them for a few days or weeks, and you could be basically safe forever for those you know.
Yeah, so if something comes closer to us, what is sort of the status quo technologies and thoughts in terms of diverting it or eliminating the threat? What are the things that one could do?
So that's a good question. It's one of the things that the Planetary Defense Conference did well. That's a of the community that is happening every 2 years, and it basically gathers scientists that are not just observing the asteroids but also preparing missions that will eventually hopefully save us from the rockets. This conference every 2 years there is a simulation of impacts, and so basically the JPL people at the Center for NEO Studies prepare an impact that is totally day of a conference. They progress the situation. They simulate, like, just imagine that this year you discover an object that is going to hit the Earth in 10 years from now, but you only have the first few days of the, and you basically uncertainty is very large, so that object would still kind of pass around the Earth, so you don't know. And as the time progresses, they simulate and more data is coming to the Earth, not just observational, but and you are becoming more certain that object is going to hit the Earth, and you can even define an area on the surface of the Earth where it is going to hit, so you can nail down the area that will be impacted. And then what the community is doing, they are trying to plan, let's say, rescue efforts, like what kind of a space mission can you prepare to save the Earth. So currently the best kind of simulated scenario is to use so-called kinetic impactors to hit the Earth, but you still need like many years before the impact to change the orbit of the object really by a very small fraction, to change the trajectory in a way like the object won't hit the Earth 10 years, let's say, in the future. So that's, but I also have to stretch out, like we still will need to have like 10 or 15 years at least time to prepare such a mission and be sure the object is going to hit the Earth and where and how. So it's not easy. I think that in these conferences we are getting closer to the realization if such a thing will happen.
So kinetic impactor. So this is some sort of a massive aircraft sent over to essentially impact the object. The change we need to effect is very small, right? Especially if you have 3 years of time between the object and the Earth. So the change we need to effect is very small, but it's still sort of mind-boggling that you can send an aircraft of some size to actually change an asteroid's path. So what is sort of what is the mass of this impactor? What would be sort of the range of the mass that you're thinking about?
So basically, you can imagine it as a spacecraft. So basically, it's like a space mission, taking a sample or landing or just flying by around. You just need to hit it pretty much. So it's not really important to have like massive amounts of instruments on its surface to do any research. So the idea is as possible spacecraft that will hit the surface basically face on at the highest velocity possible. So it's not much about the mass, it's about the velocity more. As I mentioned, kinetic energy is proportional to the velocity, which they did properly at the given time and change the velocity of an asteroid a little bit. And the reason why this is a small amount is because the mass of an asteroid is definitely much larger order of spacecraft it would hit it. So if we are talking about spacecraft, it's probably only a few tons. So that's a tiny spacecraft. You can compare it to the school bus, let's say, right? And that will hit the dust, and the change is small in the orbit at the moment of impact, but that change will change over, let's say, a decade. And it could be enough. It will basically go around the Earth very closely, very nearby, but it won't hit the Earth. That's the kinetic impactor. And if we are in a need, we could have like 2, 3, or 4 kinetic impactors to hit the asteroid and change its orbit. But it's very difficult in a sense, like in the simulations. The problem is that the small could be such a small change in the velocity of the asteroid. You are not even sure if it was enough, to change its orbit, because you don't even know what changed. You would know in a year or two, and then you are getting closer and closer to the potential impact. And if you imagine Earth flying in space, you can basically draw around it, right? Target represents the size of the uncertainty, and the target is usually much larger than the Earth itself. So what we are trying to achieve in asteroid collision avoidance is to move, not about shrinking the target down, because if you are unlucky, you will just shrink it down onto the surface of the Earth, and it will basically become like 100% certain, like it's going to hit the Earth. You just need to move that. So that's the purpose of the kinetic impactor.
I know that there are some ideas, lasers or sun energy to sort of ablate away part of the object. Is that technically feasible? Is it a possibility?
So there are definitely other options, but from the current standpoint of our technological advances, I think impact, because all the solar solutions and lasers seem very nice and probably look like from a science fiction movie and could do something, but I'm not sure if we have this maybe 30 years from now. It's all the same, like we are talking about asteroid mining and space resources. Like we still don't have the technology. It may be an option like 30 from now, but now just imagine we have like 10 or 20 years. If an object such like that is discovered, we can probably forget about any lasers.
Yeah, so kinetic impactor is sort of the more mature technology that we have, but that requires us to identify the object early enough, right? For that.
Exactly.
Yeah.
So that's why.
Yeah, right.
So that's why number is actually our devices. Even though that option is not very popular in the sense of the United Nations and cooperation of other nations, because in defense, this is not just the case for a single country to deal with. It's basically the case for entire world to do something together, because there are at least several nations around the world that are capable of launch a spacecraft and do something collision that may happen. So like nuclear explosion that should not like be implanted on the surface, but be like nearby of an asteroid, could be enough not to destroy an asteroid, but again, I will stress out changing its orbit.
So this is sending a nuclear bomb and you explode it close to the asteroid. So the shock wave basically pushes it a little bit, right? But you have to.
Yeah, well, it's shock wave. It's not really about the shock wave. It's about the energy to get kind of deposited on the surface of the asteroid. So maybe you will evaporate a portion of the surface, but the energy will, from the surface kind of bounce back. So it will create a little push from the surface. So the goal is not to destroy it with the explosion. The goal is kind of to change it direction. And danger for the explosion that will cause like disruption into multiple pieces you don't know what will be the outcome of such an explosion. So if you are unlucky, you will just break it into 2 or 3 parts, and all of them will hit the surface of the Earth, which could be if asteroid is hitting the Earth.
So what would be sort of the horizon, Peter, that you would consider to be sort of a near miss? Clearly, you don't want it to come through the atmosphere. You want it far away from the atmosphere. So what is the diameter that you want it, kind of a safety perspective to miss the target?
So basically that depends on the asteroid and the velocity itself. So the mean velocity is basically should be at least 1.4 radius. So it should be at least like half a radius of the Earth. Of course, that number it's basically velocity by asteroids, because in the celestial dynamics, if the asteroid is going around the Earth is going to attract the asteroid even closer to it, to the surface of the Earth. So you need to be sure to account of. So that's why we are talking about safe miss. So as also in the terms of the objects moving in space, you always have some kind of uncertainty around its position.
It could get into sort of an orbit around the Earth too, right?
Yes, yeah. So you need to be certain in a way, like you need to take into account also the uncertainty, like to be outside of the Earth plus the uncertainty to be certain that this is not going to hit us.
Right. Yeah, I have seen some speculation that you could actually put that into an orbit around the Earth, and then you can mine it. Is that a possibility?
That's really difficult to imagine. And one of the reasons is that asteroids are really kind of flying around the Earth all the time, around very close. I mean, we have definitely dozens of close encounters closer than the orbit of the moon, like every single year. But those kind of encounters are pretty large velocity if you compare it to the Earth itself. So it's kind of improbable you can slow the asteroid down and kind of bring it to the orbit of the Earth. But there is a special case of objects I can mention. Those are minimum. So some asteroids tend to have orbits that are very similar to the orbit of the Earth, and they can naturally get around the orbit of the Earth at least for a small time. It means like for weeks or months. So they kind of appear as satellites for a few months. So those objects are definitely the easiest for accessibility from the Earth by spacecraft or mining. Unfortunately, the probability mostly we are talking about objects that are like a few meters in size. So it's like some object that is like 1, 2, 3 meters in size that is around the Earth maybe at any given time.
And I know that there are a couple of objects that people are worried about. One sort of in 2028. What is the dimension of that one that sort of worrying that's getting closer to us?
What is the name? Can you remind me that?
I believe that in 2028.
Yes. So it should be probably asteroid Apophis that was kind of in the media quite often. And the idea was 29. It's supposed to have a very near approach around the Earth. And in 2036, there was a prediction that it could hit the Earth. Of course, the impact probability was very small in 36. But it kind of depended on the close approach in 2029, how it will go in 7 years later. And I think thanks to this Apophis, the community got a really large boost, and the research probability and the Earth, the protection of the Earth became more apparent. So I think we can thank to discovery of this object that the community got much stronger, and really the interest went about how to protect the Earth. And basically, we are safe from this asteroid, we can say, at least for the next 200 years, because we added so many more observations of this object, not just from the surface of the Earth, from telescopes, the radio telescope. We improved the orbit so much that we know it won't hit the Earth in 2036.
So when it goes past the Earth, it could go past the sun and essentially come back. So
Yes.
the possibility there is on the return path that it could come closer or could hit, right? That's the issue.
Exactly, are also kind of an orbits that kind of return back regularly, and this is the case of Apophis exactly. So they have resonant orbits, so they go to back every 2 or 3 revolutions. So I would say lucky or unlucky at the same time that this object is going to go close to the Earth all the time, because number one, those orbits intersect basically at a pretty same part of the space. But on the other hand, you can have like intersect, but those objects can never meet, right? Like statistically. But the object like Apophis will just go where the Earth is in that intersection, like quite often, like statistically. So unlucky that we are going to meet this asteroid pretty often. And from the perspective of the impact on the Earth, scientists kind of discovered so-called keyholes, and like space, if the asteroid goes through these keyholes, let's say in 2029, it will mean that it will hit the Earth in 2036. So they kind of figure out the impact such a simple thing to calculate, because of the uncertainties you have on the orbit and the position of the object. They kind of predicted, they basically mapped the area around the Earth. Like if the asteroid goes exactly around this place, 29, it will hit in 20, and in 2036 it will go again very close around the Earth. So again, there will be some keyholes around. If it goes through these keyholes, it will hit again in like 30 years later. So that's why we need to know the position of objects like these very accurately. So I'm pretty sure this object will be on the media and radar for some time.
Yeah, one thing I don't quite understand is, so when it goes close to the Earth on the way toward the sun, um, as it goes around, wouldn't it lose a lot of material? So it won't lose material? Okay.
No, not at all. So that's the difference between asteroids and comets. So you can basically imagine asteroid as being a piece of rock, a solid body. And you are right. I mean, it may go closer to the sun as the Earth goes, so the temperature on the surface can go up. But even like 50 or 100 degrees in the open space in the vacuum is not enough to evaporate any substantial or any macroscopic matter from its surface. So it's only the comets, they significantly lose a portion of the surface. Like from a typical comet, it loses every single revolution around the sun, like dozens of meters of its surface. It really goes away from a comet because it's mostly ices and dust that goes away. Like asteroids are rock solid.
So we can be reasonably certain if it goes through the keyhole on the return back, it is going to hit us. But that is sort of a 7-year sort of horizon, right? That impact would happen. Mm-hmm. So I guess during that time you can do something, perhaps.
Yes.
Yeah. So.
But like we are really safe from Apophis. It's not going to hit any keyhole in 2029. So we are safe in 2036 from Apophis.
Yeah. So I want to finish up with one of your papers, the statistical analysis of astrometric errors for the most productive asteroid surveys. So you say we performed a statistical analysis of the astrometric errors for the major asteroid surveys. So what are the errors we're talking about here? It is sort of the precision of what we are computing?
Exactly. So basically, the position of an asteroid, the asteroid is moving and the stars are not moving in your telescope. So when your telescope is pointed on the sky, so basically you are simulating the motion of the Earth. So basically you see the stars that in your image, and the object is moving in the solar system because it goes around the sun. And you measure the position of the asteroid with respect to the stars. So you have the coordinates in terms of right ascension and declination. It's very similar to you maybe during the high school, you measure something on a paper, you have a position in X and Y, but you can always provide what is the uncertainty of your measurement. And it's usually given with your rule, right? Like it only has like inches, so you position is accurate to this degree, right? That's your measurement. So basically what observers do, they provide to us not just the position on the sky, sometimes they provide to us the uncertainty on their measurement. But the problem is, back, there was no information on the uncertainties whatsoever, so they just sent positions to us, right? So this is our position on the sky, right? Ascension or declination. You can information on uncertainty. So you could still kind of derive the orbit, and basically how the orbit fits the data, that gave you the deltas on the position, right, ascension and declination. And information, for instance, you see like surveys that use larger telescopes with longer focal length had naturally much smaller errors on the measurements, or telescopes that were smaller and had large pixel cameras, larger errors. And you could discover things like some telescope had issues with time, right? So they were reporting time to us with an error of 1 or 5 seconds. So you could see that in the data, right? Or they were measuring objects that were near the Earth, like near-Earth objects. And if they move in your image and your exposure time is longer, instead of the point spread function image, like, you know, the asteroid looks like the star that moves, you have a basically, because in like few minutes of exposure, it makes a line on a screen. And basically, astronomers usually had during that line, so they had much larger error that was along the track with respect to across the track. So what we did in our paper, we basically measured, after fitting the orbits of all the asteroids through the data, like what are the errors for the most productive asteroids? Because MPC is our Minor Planet Center, has a list of 2,300 observatories around the Earth, like all around the Earth, including observatories. So we could assign like what is a typical error, measurement error for every single observatory. Or some of them we even kind of splitted those errors as a function of time. Because some observatories are functioning for decades. You could see in the data, like in 1990, they started to using the CCD camera. In 2020, they probably changed the camera for a new camera. You can see data. If you know the uncertainties, you can kind of, you know, turn the knob of the orbit fitting, like, okay, so you can weight these data more because they are more important. They are definitely accurate. And these data from this side, other astronomers, or maybe from some older survey that had some issues, you can kind of downweight when you are computing the orbits. And that this is very important for especially things like, you know, Earth and frequency and stuff like that. Especially if an object is maybe going to hit the Earth, it's very, very important to know like what is the uncertainty on the orbit, and also understand the uncertainty. So you get up from the numbers that were provided to us and what we can say back about the data. So basically, maybe to kind of conclude, what was the conclusion of my paper? It was basically for a given observatory site in right ascension and declination. So it was kind of a weighting scheme that people are using, I think, now around the world from my paper. If there are orbits, the data from the Minor Planet Center, then they can weight the data according to the weighting scheme I created in that paper.
So as more data, as we collect more data, we can sort of look at cross-sectionally and get some better idea of accuracy and errors and precision. So in conclusion, Peter, dinosaurs unfortunately did not have telescopes. We seem to have better equipment, but we are not completely there yet. We still haven't really cataloged all the near Earth objects. We seem to know all the big things out there. That's pretty good. And technology, we talked about the kinetic impact as possibly the only mature technology we could deploy if something comes closer. What is the horizon, you think? How many years do we need? I'm just asking you to speculate. How many years, how many decades would we need to be sort of in a position to say, whatever happens, we either have a technology to divert it, we have cataloged everything that might come closer, we'll have sufficient time to react. What would be that time you think that we need?
So that's an excellent question because, again, results from these questions in one of my papers. So basically, one part of my work was to simulate the new telescope being built in. Its original name was LSST, a Large Synoptic Survey Telescope. It was now renamed to Vera Rubin Observatory. It's a giant telescope that has an 8-meter size mirror, and its goal is to scan the entire sky. I mean, there are larger telescopes around the world, like Keck with 10-meter size, Gran Canaria 11-meter size, but this telescope is not going to observe one single object for many hours. It's just going to scan the entire sky. And of course, its primary mission is dark. It will also provide data on the minor planets of the solar system. So my goal in this work was to kind of compute how many of these near-Earth objects are we going to discover with this large telescope. It will be a lot. It will significantly help us in achieve this goal. So if we don't have this telescope, it will take more than 10 years to get closer to that 90% goal of finding objects larger than 140 meters. We probably 10 years our original schedule, because right now we are at 40%. And again, I have to mention these are objects larger than 140 meters. I'm not talking about smaller objects. But that's not all. So stay tuned. This study is next year. So fingers crossed, like for LSST, and now called Vera Rubin Observatory. And that's not all. NASA also invested a lot of funds and money into the new space telescope that is called NEO Survey or Near Earth, which is a new infrared telescope that should go to space, hopefully in the next 3 or 4 years. So together with LSST, Vera Rubin, the NEO Survey mission will kind of work in a tandem, like Vera looking in the sky at night toward the opposition, and the space telescope, the NEOSM, looking kind of toward the morning and evening parts of the sky. So together they can achieve this goal in probably 6 years. So fingers crossed for these two missions that are basically key missions for the future near-Earth object discoveries.
Yeah, so a few decades, it sounds like, I guess detection and cataloging, getting closer and closer to 100% is the key, right? So
yes,
if you have sufficient time, then you could do something about it. If you have sufficient time, that is really the key, isn't it?
Yes. Hopefully, I would say until 2030, we have like 90% objects cataloged larger than 100 meters. And of course, we have other projects. I will only talk expensive, like a space telescope and a giant Vera Rubin Observatory in Chile. But there is another project that is ongoing for a few years already in Hawaii that is called Atlas, which is totally opposite telescope. It's like, wow, a small telescope is only 50 centimeters in size, its mirror. So it's a telescope that maybe some amateur astronomers have in their backyards in terms of size. But of course, the point is it's not that simple. It's a large field of view. It scans the entire sky. It's on great location. It's on Hawaii, so it has excellent sky conditions. It's very dark, and it's not all. So they have a pair of telescopes there. They have pairs of telescopes. They South Africa, pairs of telescopes also in Chile, Australia. So the plan for this small telescope is to see those objects that are going to impact the Earth and pose imminent impact. Like you have 1, 2, or 3 weeks before the impact. It's for the small objects, like objects are like 10, 20, 30 meters in size. So for those, maybe not even the large telescope, like space telescopes are not going to discover all like 10 years. But with these small telescopes like Atlas, you can see them 1, 2, or 3 weeks before the impacts. These objects do not really pose a threat in a sense like they are going to destroy the continent. They're not going to, they can destroy a city, like in terms of like Chelyabinsk, right? But if you see them 1 or 2 weeks before impact, that's plenty of time for us to give us exact information they are going to impact this location, evacuate the people from that area and prepare for that impact. So that's also a very important part.
Yeah. I know that there are a lot of amateur astronomers looking for these objects too. Is there some sort of a network of amateur astronomers and some sort of web-based cataloging going on of these objects?
Indeed, it is. So even when you look at the discoveries the last 2 decades, like professionals really took like the 95% all the discoveries. I have to mention, it's a lot of funds, especially from NASA and large telescopes. They're working in this field. The minor base of 2,300 observatories. Many of them historical, they don't work anymore. But most of these observatories are amateur astronomers. So sometimes they really contribute discoveries because it's difficult to compete with these large telescopes, but they are very valuable in follow-up, let's say. So because I tend to say there is no discovery without follow-up, because when you see the object for the first time, just the first, 4 positions, you all know, and that's all you can say about the object. You don't know the orbit. You don't even know it's a near object. You don't know anything. So that's why you need more data. You need the second, third, fourth, and fifth night. That maybe sounds some kind of a boring activity for professionals. So I would say amateur astronomers are really important in providing follow-up, and sometimes they are looking in places where professionals are not looking. So I would say amateur astronomers are still quite important. Individuals telescope at great sites, let's say on Southern Hemisphere or in Australia in some dark places. And very valuable parts of the sky are, as I mentioned, when you look from the Southern Hemisphere, or if you after sunset or before sunrise, at the dawn or dusk, because the sky is not dark enough. So large telescopes don't even start operations because they say like, it's not really worth to start. So hitting sun, but that's where the amateur astronomers are looking, and they still discover comets, let's say, in that area of the sky. They can discover interesting objects, like objects that are in the inside of the Earth's orbit. And I would say recently there is one new network of commercial telescopes called Unistellar. They have a digital telescope on market that people purchased. I think they sold several thousands, and they for the people who can just bring the telescope outdoors and on the computer, or basically on your cell phone or tablet. You just type a name of the object if there is a campaign, and the same are automatically pointed out to that object, and data can be sent to the Minor Planet Center. So I would also say it's not just the professionals, but we also rely on amateur astronomers. And I think for amateur astronomers, it's still a part of the research, but fun activities, because you can still discover your own object, your own asteroids, your own comet. So I think it's still amazing, right? If you are such a person having a small telescope, discover in 2021.
Yeah, it seems like it's sort of a crowdsourcing data, and it seems like it's in a few tens of meters size objects, right? They're not going to create worldwide problems, but they could still be quite catastrophic for if it falls in the water, it could be tsunami and those types of things, right? So yeah, and there's a huge opportunity for crowdsourcing. Yeah.
Yeah. I would also add another maybe information. So we were talking only about like telescopic observations, like you are an amateur astronomer here who has his small with a camera. But what is also kind of interesting, recently in the last, let's say 5 or 10 years, professional surveys started to they really started to publish their data, large archives in terms of images. It's a vast quantity of large CCD images they put online. It's not just for the scientists who can really go back and just sift through the data, amateur astronomers who are doing archival discoveries. Because often in the past, like 10 or 15 years ago, even nowadays, most of the discoveries done in those large surveys is done automatically. It's a computer software images and finds moving targets, but software is still not on the level of the human eye, because of course those amateurs often spend hours just looking on the images and looking, and they are pretty sure that 100 objects they see moving, they were already reported, so there is no point of reporting them. And suddenly they see this very faint streak going through the images, and they're going to us from years ago, and we'll tell them, yes, it's an unknown object. It was never reported from this large telescope. So amateur astronomers are not just observing fresh, they can go back to archives and they are submitting years ago large surveys because the surveys made the data public. So they can even make discoveries of objects that were observed years ago. And if not discoveries, they can extend the arc of the object that was having discoveries since 2000, let's say, but they can extend the arc many years back, which makes the orbit more accurate. So those are examples like how ordinary people can go and make discoveries they don't have.
Yeah. Excellent. Excellent, Peter. This has been great. Thanks so much for spending time with me.
No, thank you very much for having me here.